So hello and welcome student to the today's lecture, and this is our class course number MA412 linear algebra, and this is lecture number 34. Okay, so now recall that in yesterday's or last talks we discussed about orthogonal projections. We showed that orthogonal projections are actually self-adjoint operators. Okay, and if you have projection which is also self-adjoint, it has to be orthogonal projections. That is even only condition. Okay, and there are, we can also show some examples. Now today we will discuss one of the most important theorems. Is called the spectral decomposition theorem. The spectral decomposition theorem, or some people call spectral theorem only, for normal / self-adjoint operators. Okay, and so what is the theorem tells you about this? So suppose we have a okay, so let me write down the statement. So let V be a finite dimensional inner product space and you have a linear operator on V. Okay, and V says that, maybe let me write down some more things, says that D has C1, C2, some Ck as distinct eigenvalues. And these eigenvalues are in F is the underlying field. It can be complex number or it can be real numbers also. Okay, so now there are two cases. For the case when it is real number, we have to assume that T is self-adjoint, and for the case when if is complex number, we have to assume that T is normal operator. Okay, and then obviously so let T is self-adjoint for F equal to R real number and TB not is TB self-adjoint, and normal for complex field of complex number. Okay, so this is my assumption. So under this assumption, so and obviously there are many other properties let us assume. So because self-adjoint operators, so when R is if is C and T is normal operator, then we know that over complex field, normal operator tells you that it has the vector space has a basis consists of so the basis which is also orthonormal, and this consists of eigenvectors of T, and when it is the field is real number, then the same property is there for self-adjoint operators, right? So okay, so this is already known. So now assuming that let the eigenspaces Wi be the eigenspaces of T corresponding to the eigenvalue corresponding to the eigenvalues. What are the eigenvalues? The C1, C2, and Ck. These are the eigenvalues. Okay, and so you take the orthogonal projections. Now we define it. The third, say, maybe let me write down. Say Ti's are orthogonal. It's a non Wi. Okay. So these are all the conditions. If this condition happened, then what happened? Obviously, so this condition tells you that number one, then and the following are true. What are the following? Number one, you can write down V is a direct sum of this Wi's equal to 1 to k. Okay, so these are the eigenspaces corresponding to eigenvalues C1, C2, Ck. And then number two, obviously, if you write down, say, the Wi dash, which is kind of, you take sum over I equal to j equal to 1 to k, but j not equal to I. Wi. So you take all the Wi, all the Wj's instead of Wi. So what does that mean? That means W1 dash equal to W2 plus W3 plus Wk. There is no W1 here. Okay, so j not equal to I. So if you choose this, then actually this is actually orthogonal perpendicular. Wi dash is nothing but Wi perp. Okay, so this is orthogonal perpendicular to Wi. Okay, for each I. This is true for all I equal to 1 to k. Okay, for each I. Okay, so decomposition. So not only V is a direct sum of those Wi's. In fact, it is these direct sums has very nice properties. If you take particular one, then some of the other rest of those things will be the orthogonal complement of this that particular vector subspace. Okay, so this property is a very important property. And now property number 3 is that these projections, so they are kind of actually chronicle delta. So what does that mean? That means if you take this, that will be Ti delta ij Ti. Okay, this is for all I. 1 less than equal to I less than equal to for all ij. So they follow this chronicle delta. And number 4 is what? Number 4 is that the identity operator can be written as direct sum of T1, T2, so Tk. So it's kind of direct sum of these operators, these projection operators, and this is called resolution of identity. So it's called resolution distribution of the identity operator okay. And finally, whatever is final one, which is actually called spectral decomposition, and that is what that is that the most important that T can be written as direct sum of the C1 T1 plus C2 T2 and so on CK TK. Okay, and this is called the spectral decomposition. Spectral decomposition of T. So you recall we did it for diagonal level operators. So similar thing is true here, but here something more is true that so when you take orthogonal projection, something more is true. Okay. So now we need to prove for these statements, and then obviously this theorem has lots of applications. So maybe we will prove one by one some of those. So now, so let me prove maybe one by one. Proof. So what was the first statement? That you can write down V direct sum of the Ws, and that is obvious because so you recall that from Schur's theorem we proved two important theorems. One is for a complex in a product space, complex finite in a product space. Normality is equivalent to saying the existence of orthogonal basis of eigenvectors. Okay, and similar thing is true for self-adjoint operator for real vector space. Okay, real finite vector space. Okay, so so in any case, if it is normal or self-adjoint, whatever. So this is to define cases. Obviously, it's for this is for f equal to c. This is for f equal to r. Okay. In any case, what do you know? So V has an orthonormal basis consisting of eigenvectors of T, right? So if you have an eigen basis whose elements eigenvector of T, that means T is diagonalizable. So T is diagonalizable. Okay, and thus we prove it long way ago. If T is diagonalizable, that is equivalent to saying that the eigenspaces of actually direct sum B direct sum eigenspaces. Okay, right? Thus you can write down that B equal to direct sum of these eigenspaces Wi equal to 1 to k. Okay, so this is a proof. Okay, so now to prove the second one. So this is W. So what is given? Wi dash equal to summation j equal to 1 to k and j not equal to I, whatever I not equal to I, wj. Okay, this sum. And then I need to prove that is actually so what is claim? So claim is that this Wi dash is nothing but Wi part is perpendicular. So what does that mean? That means so every element of Wi dash is perpendicular to Wi, right? So on the other way, every element of W is a orthogonal to wi dash, right? So what does that mean? So let's choose that. So let you choose some v belongs to wi, and any other things you belong to j, well, j not equal to I, okay, other than the eigenspace. You choose anything, then whatever, then obviously you know that because then u and v are orthogonal. Why? Because they are the eigenvector corresponding to distinct eigenvalues, right? wi is eigenspace of ci and wj is eigenspace of cj, right? So they are orthogonal as they are eigenvectors corresponding to distinct eigenvalues, right? Distinct eigenvalues, the ci and cj, okay, ci are distinct, and then so that means that this v and u, they are actually 0, and that is true for every j. So this is for all j not equal to I, right? For any, if you choose any eigenspace which is other than wi, so every element of wi is orthogonal to that, right? So what does that mean? That means if we choose, so let you choose any vector, say x belongs to wi dash, and then you can write down x equal to this direct sum of say maybe ui I equal to uj, j equal to 1 to k, and j not equal to I. They cannot be equal to I, right? So that is ui dash. So now then obviously you can write down, you can choose what is the inner product of v with x. Now you see that this is so by direct sum I mean some addition of those elements, u1 e to that, right? Now if you write down, then obviously it will be what? It will be direct sum of v. Okay, so let me write down one more step, then it will be easier. So we have v comma this direct sum of say uj, j equal to 1 to k, and j not equal to I, right? But then you just additive property of inner product tells you that is the sum of j equal to 1 to k, j not equal to I, v comma uj, right? But we just proved that whenever v and uj are on the different eigen spaces, then they are orthogonal, right? So each of those are 0, so this will give you 0. So that means v is orthogonal to every vector of wi dash, and that tells you that so this is one way of saying that every element of w dash, okay, so yeah, so if you choose any vector x from this, so that's orthogonal to v, and thus wi dash is actually subset of wi par, right? So why? Because you choose any arbitrary vector which is inside wi dash, and you showed that is orthogonal to v, and v is, so this is for any v belongs to w, right? V is also arbitrary. So that tells you that wi dash is actually subset of wi par. So element of wi dash are orthogonal to wi. Is that okay? Now I have to sort that also. They are, this is actually same subspace, so this is proper, this is not proper subspace, this is equal the total subspace, then I am done, right? But that is obvious because you recall that what is this Wi part, so this is direct sum of Wi or Wj, j equal to 1 to k and j not equal to I. Okay, so what does that mean? That means this is everything finite dimensional, and you know that for direct sum the dimension of so this is, sorry, double dash, the direct sum of this nothing but the sum of the dimension, right? Sum of the dimension of Wj, j equal to 1 to k and j not equal to I. Okay, what does that mean? That means only one subspace is not there. So if you add one subspace, that will be the full dimension of full vector space, right? So it will be nothing but V minus dimension of Wi. You're just adding dimension Wi here and subtracting. But again, so this is because W is fine, V finite dimensional, and B minus dimension B is nothing but the dimension of Wi part. Okay, so what does that mean? That means dimension of Wi dash is equal to dimension of Wi part, and they are also substitute that, and with these two property, this implies that Wi dash is nothing but Wi part. They are perpendicular to each other, right? Because when you have proper subspace on a finite vector space, then the dimension has to be at least less than that, right? But here dimension is same, so this subspace cannot be proper subspace, it has to be the full subspace, so they has to be equal. Okay, remember this is for finite dimensional vector space. If you're not finite dimensional, then this property is not true. Okay, now okay, so now let us prove the third property, that tells you that when you take Ti and Tj, what is the value of that? So obviously when I equal to j, so Ti Tj equal to Ti square if I equal to j. Okay, but these are projection, orthogonal projection, so that means this is Ti. Okay, obviously you can write in one time Ti. Okay, now if I not equal to j, then what happened? Then you see that you so you write down a vector v, you choose a vector v, and then you know that this is direct sum of this Wi is I equal to 1 to k, right? So every v can be written as some direct sum of small vi's, small wi's can be, okay, I equal to 1 to k. So what does that mean? That means b is direct sum, b is sum of W1, W2, Wk, where small w1 equal to inside capital W1. Okay, and then if you evaluate that v on here, then what happened? Then Tj is a orthogonal projection or jth component, right? Wj. So this will ended up to gives you Ti of Wj. Okay, so Wj is inside, the small Wj is inside capital Wj, that eigenspace corresponded to Cj. Now because Ti is orthogonal projections on Wi, so this is inside the kernel of Ti, right? So this implies this is 0, as Wj is actually belongs to null space of Ti, right? Is that okay? Because the range of Ti is Wi, and the complement of null is the complement of range is the null space, right? For finite vector space, as I proved that these Ti's are projections, right? So now we combine this 1 and 2, you will get the result that Ti and Tj is nothing but delta Ij and Ti. Okay, This is obvious. Okay. So now we have this fourth one that going to prove the resolution. So so how do you prove that it is in the resolution? So you start with, so you know that this obviously is TIs. So for any v, you can write down obviously for each T, you can write down range of TIs plus rejection of null space of Ti, right? That we proved in last lectures. Okay, and because TIs are orthogonal projections, so as TIs are orthogonal projections, what do you know? We know that this range of over null space of Ti is actually orthogonal to range of Ti. Okay, and range of Ti is what? Range of Ti is equal to Wi. So Wi orthogonal, but W orthogonal is nothing but Wi dash. That we already proved in the second term, right? So what does that mean? That means if you choose any vector from V, and so if you choose any vector, say V equal to say V1 plus V2 plus dot Vk is the element of V, which is injection of Wi equal to 1 to k, and then if you apply your Ti on V, so you will have Vi, and Vi is the element of Wi, right? So what does that mean? So this means that every element of Ti send Vi to V. Now with the help of this, what you can say, you can say that you can write down so from this equation you can write down that V will be equal to, so V1 can be written as T1 of V, and similarly T2 is equal to T2 of V, and so on, and Vk will be Tk of V, right? Because of this fact, Ti of V equal to Vi. Vi I am writing by Ti of V. So what does that mean? That means you can write down this identity of V equal to T1 plus dot Tk of V, right? This is true for all V belongs to V. So what does that mean? That means the sum of this operator is actually nothing but the identity. So that means that identity operator is actually sum of these projections operators. Okay, and this is the theorem proof. Okay, so this is the resolution of the identity operator. Okay. Okay, now finally we need to prove the spectral decomposition theorem, whatever that I mean the most important theorems. And spectral decomposition theorems, how do you prove? So proof is not also very difficult. So you start with the V, and then you know that you can write down this V1, V2, Vk. Okay, because we should direct sum of those. So and here this Vi is an element of say Wi's. Okay. And then we can write down my T of V is nothing but T of V1 plus dot T of Vk, right? Is adding those things, but T is V1 is the eigenvector corresponding to eigenvalue C1, so you can write down this is C1 V1, and next one will be C2 V2, and so on, and the last one will be Ck Vk, right? So what does that mean? That means you can write down C1, V1, C2, V2, and Ck Vk, and you know that V1 is nothing but also this is T1 of V. You get on T1 this projection of V on W1, right? So the image of T1, image of V and T1 will be capital small V1, and similarly C2 of T2 of V, and so on. And the last one will be Ck of Tk of V, right? So again you can write down this is C1 T1 plus C2 T2, and so on, Ck Tk of V. So thus this is for all, obviously for all v belongs to v, and so we can write down t equal to c1 t1 and some dot 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 ck tk. Okay, so this is spectral decomposition. Spectral decomposition. Because this C1, C2, CK forms something called point spectrum, okay, of T. Okay, so done. So this is that proof of the theorem that you can actually write it down each of those vectors in terms of sum of the spectral decompositions. Now obviously, so you can have a so let me write down a remark. So what is immediate remark tells you that how the matrix representation look like. So suppose you have say bi's are say basis. So you can choose orthonormal basis, okay, no problem. So orthonormal basis of wi's, okay. And then you write down B is the union of bi's. I equal to 1, 2. K. So obviously this B will be also your orthonormal basis. Okay. And here suppose I am choosing that this dimension of my wi's are say mi's. This is something called algebraic multiplicity of Ci, right? So dimension of the full vector space. And that this is nothing but this summation I equal to 1 to k. Okay, now with the help of that, how this matrix of T look like with respect to this basis B, this is obvious now. So T with respect to this orthogonal basis B will be what? So it is break into the smaller things, right? These kind of, okay, and then these, okay. So you'll have here C1 into say IM1. So IM1 is that identity matrix of M1 cos M1. So because why I choose M1? Because M1 is the dimension of W1. So from W1 I am getting these matrices, and on W1 this is projection, right? And you know that projection operators so the projection operators the eigenvalues are 0 and plus 1, right? So this is so 0 will come here, dot 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 dot, plus 1 will come here, right? So this similarly it will be CQ I2 and so on, dot dot dot, last one will be CK IK. So this is a nice matrix composition. So for example, you can choose, so let me write down 6 cross matrix maybe. So suppose there are eigenvalues 1, 2 and 3 with algebraic 2 to 2. So this can be 1, 1, 0, 0, then 2, 0, 0, 2, and maybe 3, 0, 0, 3, and rest will be 0, everything 0, okay. So the diagonal will be 1, 1, 2, 2, 3, 3, and rest will be 0, right? So this matrix is coming from that eigenspace W1, this matrix coming from eigenspace W2, and so on, okay. If there are eigenvalues are like if that characteristic polynomial is of this form. This is the characteristic polynomial. Okay, so now obviously there are many applications of this theorem, like lots of applications. So obvious fact that whenever you have a linear operator T, and then if you get, okay, so this is obviously one remark. So another maybe corollary directly. that if you have if spectral decomposition is given, and then so if say t equal to something c1 t1 ck tk, and then what happens then for any polynomial. So this is a polynomial algebra or the same field f, or you can write down pn of f, whatever. If you want to evaluate what is the value of g, what is the value of t on g operator, so this will be a new operator t, but this is more easy. Why this is more easy? So this is nothing but g of c1 into t1 and so on. And the last one will be g of ck and tk. So spectral decomposition immediately tells you what happened, what will be the operator gt look like. Okay, so g is a polynomial, and when you value t and g, it will be again a polynomial. But because of the spectral decomposition, it is so nice. Immediately you will say that. Otherwise, it may be very difficult to find out this power of this, right? Okay. Obviously, the proof and proof is also not difficult. So suppose we have say gx polynomial, something say ci xi I equal to say 1 to something m, whatever you choose, some power. Okay, suppose this is the polynomial and with variable x and degree say n. Okay, or maybe you can start with 0 also, I equal to 0 to m, doesn't matter. Okay, so why this g of t equal to this? So obviously what will be the g of t when you replace that? So it will be obviously ci ti, right? I equal to okay, so 1 minute. So yeah, ci ti I equal to 0 to m. But you know that it is nothing but the direct sum of is the sum of this spectral decomposition, right? So you can replace that thing. So what will be happening? So obviously that constant term will be c0 into I. Obviously there is no problem with that, and we write down I as a resolution thing one by one. Okay, and the other term will be what? So other term will be summation ci t. So for t will okay there's too many c's. Okay, maybe let me write down this is some di, otherwise yeah, so di, so this is d0, constant from d0 di, and then c1 t1 and dot ck tk to the power I, right? I equal to 1 to m. Now what is the advantage? Advantage is that so you expand this c1 ck in binomial x function, so you will have somewhere you will have c1 t1 to the power I, right? But t1 to the power I is t1 itself, because t is the orthonormal projections, t square equal to t, and hence any power of t equal to t itself, right? T square equal to t, so t cube equal to t, and hence so t power I will be equal to t, or rather sorry t power any part t power k will be equal to t power I, as ti's are orthogonal. It is true for projection, any projection actually, orthogonal projections. So what does that mean? That means when you take power, so that power ti will be this only. The only thing is that when you take, so this is one fact, and second thing is that ti tj is 0 whenever I and j is different, so there is no product term is also coming, right? So only term is coming is power terms, and then you can write down these actually. What is so you can write down the g of t is nothing but and d0 into I, so I also can write down, so you use that resolution of identity tells you that this is this, and then you'll have summation di I equal to 1 to k, and So this will be C1 power I. So C1 power I into T1, similarly C2 power I into T2, and so on. Okay, Ck power I into Tk. Now you see that if you just take the sum separately, so first term will be summation I equal to 1 to n. Okay, so T0 T1, so this is sum of T1, right? So di Ci and okay, so yes, so di Ci and then T1. Similarly, second sum is also d0 d1, so di Ci C1, yeah, so di C1. Similarly, second term is nothing but I equal to 1 to k di C2 or I with T2 and so on, right? The last term will be what? Summation I equal to 1 to k di Ck or I with Tk. But this is what? This is actually the evolution of C1 on G, right? Similarly, this evolution of C2 on G and so on. So finally you have this is GC1 T1 plus GCK TK. Okay, so exactly whatever we have claimed. So for polynomial with the spectral decomposition, it is very immediate to write down what will be the value of that operator on that polynomial. It is actually you can say that this is actually spectral decomposition of. So this is the spectral decomposition of G of T. Okay, clear? Okay, so now so there are several applications are there, so I will just give one application today and maybe some of the application maybe next class. So what is another applications that so if you start with the normal operator and then obviously over complex inner product space, then you can say how this adjoint look like. See, in general we don't know adjoint how it look like, right? But spectral decomposition tells us that if for complex inner product space and for normal operators, the adjoint of the normal operator will be a polynomial in T. Okay, and this is actually equivalent condition if and only if you start with the adjoint is polynomial T, then that T has to be normal is there also, because the polynomial in T always comments with T, right? So T star comments with T and vice versa. And these theorems require there is something called Lagrange interpolation. I hope I don't remember whether I have defined it or not, otherwise I can define it immediately. So what is Lagrange interpolation? So it tells about that. Okay, so let me first discuss Lagrange interpolation, then I will come back. So Lagrange interpolation. Okay, so okay, so let me write down interpolation. So what is that? Tells you, suppose you start with a set of some constants C0, C1 to Cn. You are in space of polynomial. Okay, so let me write in PNF. So this is space of polynomial whose degree is at most n, right? It can be constant to n. Okay, so they forms a vector space with this polynomial addition and this. And suppose you start with constant, say n plus 1 constant, and then the question is that can you actually write it down a polynomial which actually takes a fixed set of values, say b0, b1 and bn on these constants. So that means say something polynomial G such that G of Ci equal to Bi for all I equal to 0, 1 and n? The answer is yes. So you can always do it, and this method is called Lagrange interpolation method. So what is that thing? So you need to find out or define something called Lagrange's polynomial. So Lagrange's polynomial. What are the Lagrange polynomials? So Lagrange polynomial with respect to these sets, C0, C1 and Cn. So you define this polynomial like say fi of x, and this is what? This is you take product with x minus ck and ci minus ck, and k is running over 1 to n, k not equal to I. What does that mean? That means in the denominator there is no chance of it become vanishes, right? When k equal to I, it vanishes, right? So you can't define this. So you define such a way that denominator is always non-zero. Okay. Now you check that this polynomial has a special property. When you evaluate on Cj, what happens? So if you evaluate on Cj, there are two cases. Either j equal to I. So when j equal to I, and then it will be 1, because when j equal to I, then you will have x equal to ci. So cj equal to ci, right? So it will be ci minus ck, so everything get cancelled. So it's 1 if is I equal to j, and if I is not equal to j, then that term vanishes, right? Suppose I not equal to j, and for I, for j there will be a term that k will be running from 1 to n, k not equal to I, but k can be equal to j. So cj minus ck will k. Okay, so if sorry, this is equal to I equal to j, then this is I equal to j. If I not equal to j, then what happen? Then k can be equal to j, right? Because k cannot be equal to I. So there will be term here cj minus ck, right? But k can be equal to j. So one term will be cj minus cj, and doesn't matter. So if cj minus cj is there, this is 0, so it can make everything in the product 0, right? So it will be 0 if I not equal to j. This is a property, and this property actually is very kind of orthonormal kind of property. You can see, understood that, right? If I cj is delta I kind of thing. Okay, whenever delta, so it's kind of delta ij, right? Whenever I equal to j, it is 1, otherwise 0. Okay, so it is easy to just take that this forms a basis of this PNF. So this f1, f0, f1 and so on, fn actually forms it. So this is called Lagrange's basis. I mean, this basis is very important. So forms a basis for this polynomial over f. Okay, PNF. Okay, and then with respect to basis, you can write down any g in terms of summation GCI of this fi. You can just prove that. It's obvious. Okay, and you can also, obviously these FIs are obviously linearly independent, because so you choose any linear combination which is 0, that tells you that this f has to be 0 itself. I mean, the coefficient has to be 0 itself, and so you have a linear independent subset of dimension subset of finality n plus 1. So it has to be a basis of vector space of dimension n plus 1, right? So this is basis actually. So this method is called Lagrange interpolation, and that gives us the most important property. The most important applications of spectral decomposition theorem. One of the most important, obviously. Okay, so what is that? Decomposition tells you that whenever you have a normal operator on a complex and Asper space, then the adjoint is actually nothing but some polynomial in T, and that polynomial is coming from this Lagrange polynomial. So let me now write it down, the theorem or corollary, whatever maybe. So let me write down theorem of this form. So obviously, so let this is V finite dimensional inner product space whatever is given, and also so that my field is over complex number. Then what happened? Then this operator belongs to this LV is normal if and only if this T star is actually some polynomial in D for some G belongs to this polynomial algebra. Some polynomial algebra. Okay. And this is one only condition. So one part is obvious, obviously. So proof. So what is the proof? So if obviously T star, if T star equal to this, T star equal to G of T, then obviously T star will be T star T, because this is polynomial T, right? So T always comes with any polynomial T. Okay. So T is normal, like T is normal. The converse part is more important. Conversely, if T is normal, what does that mean? That means so let me start with the spectral decomposition. So let T be normal, and so for Raman operator we know that the spectral decomposition theorem exists. So let me write down that is C1 T1 and CK TK, the spectral decomposition of T, because T is normal on complex and across space. And then you can choose what about T star. So T star will be, and obviously T star will be nothing but C1 bar and T1, but T1 star. Okay, so let me write down T1 star first, but then I will come back. CK bar, TK star, but these T1, T2, TK are nothing but the orthogonal projections. Now orthogonal projections are self-adjoint, right? So we can write down this is C1 bar into T1 plus dot CK bar into TK. Okay, as Ti star equal to Ti, the self-adjoint. Okay, so so what does that mean? That means I will now choose my operation such a way that I will choose my polynomial such a way that that on the value C1 to CK, it takes the value C1 bar C2 CK bar. Then I am done. And then obviously, okay, no, this is plus, this is not star. If I choose that, then obviously T star will be this polynomial in G, right? Now choose a polynomial using Lagrange interpolation method. Lagrange, yes, interpolation method. Maybe so say G is the polynomial. So what is the property of G? So G takes value, and the value on Ci is nothing but Ci bar. So this is the polynomial I can choose. Obviously, interpolation tells me that you can do this thing, whose degree will be at most k actually, because here you have C1, C2, Ck, many options actually, or other degree will be at most k minus 1 rather, yes, because when you have degree at most k, you need k plus 1 many vectors. So the degree is the degree of G will be bounded by k minus 1. Okay. So this polynomial will be exist, and you can choose such that G of C equal to this for every I is equal to 1 to k for every I. Okay, so this is obvious. So and what happened for that? So if we apply G on T, then you know that. So from previous theorems, where is that theorem? Yeah, no. Let me put that. Yes, here you see that when you take a polynomial, we evaluate on T, then it will be of this form because T has a spectral decomposition, right? So you can think that the G of T has a spectral decomposition, and that will be nothing but G of C1 of T1 and so on, G of Ck of Tk. Okay, but we know that G of C1 taking value C1 bar, so you can write down C1 bar, C2 bar and so on, and GCK equal to CK bar and TK, but this is nothing but T star. Okay, so we choose G such that G of Ci equal to Ci bar, then this G is evaluate, this G is that polynomial such that T star equal to G of T star. Okay, so that means T star is nothing but a polynomial in G. Okay, yeah, so this is the proof, and I will stop here, and maybe in next lecture we will give some more important applications of this orthogonal, spectral decomposition theorem and orthogonal projection. Okay, let's stop here.